SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture on basic control systems for mechanical engineers. Today we are going to study about Nyquist plot. So the idea about Nyquist plot is for an open loop system we can use Nyquist plot to find the number of unstable closed loop poles. So this is our objective, that using the Nyquist plot we want to find, given an open loop system, we want to find the number of unstable closed loop poles. So before going to that, we will focus on one concept which is called the argument principle. So now let us say we have a transfer function h of s which represents an open loop system. So let us say in general form we can express it in terms of the number of the zeros divided by these poles. So in denominator we have poles. So basically there are m zeros, n poles, and we assume that n is greater than or equal to m. So all these z1, z2 up to zm are the zeros, p1, p2 all the way up to pn are the poles, and the number of poles is greater than the number of zeros. Now let us consider that we want to evaluate this h of s at s is equal to s naught. So how do we go about that is evaluate this at s is equal to s0. So since it's a complex number, there will be magnitude as well as phase. The magnitude is proportional to magnitude of 0 vectors divided by the magnitude of pole vectors. So what do we mean by 0 vectors and pole vectors? So this particular vector s minus zi, where I goes from 1 to m, is basically the 0 vector, and similarly s minus pi, I goes from 1 to n, is the pole vector. Similarly, the other aspect is the phase. So phase is basically equal to sum of all 0 angles, that is angles made by these 0 vectors, minus sum of all pole angles, and let us denote this as some alpha. So we will define this as alpha. So now let us consider in the S plane any particular. So say we have a particular system in the S plane whose pole 0 map looks something of this form. So this is basically the pole 0 map. And what we are going to do is we are going to evaluate at S naught. So what we first we do, we construct these vectors. So these are the 0 vectors, and here we have the pole vectors, and then we calculate these angles. So this angle which is basically formed here will be theta 1, this will be theta 2, this will be, let's say, phi 2, and this is phi 1. So in this case, in this manner, we can select any point S0 and calculate the angles and similarly the magnitude, and that constitutes the evaluation of this h of s at s is equal to S0. Now let us say, let us keep on evaluating this about some contour. So for example, let us consider we are evaluating about this particular contour, and the contour follows this particular direction. And this is the S plane. Now once we evaluate, we will still get a complex number, right? So we can create a plane for this h of s. So this is the real part, this is the imaginary part. So now if we at each point we keep on evaluating this contour, we will get a contour which on this h of s which looks something of this form. And this is the direction which this contour follows. So this represents basically h of s in this plane, and corresponding to this S naught, we will have a point here which we can denote as S naught cap. So basically you will see in this case, this alpha what we have, that is the phase, will be have limits, and this alpha will lie between alpha lies between alpha mean and alpha max. So here we have seen that alpha lies between alpha mean and alpha max. Now let us consider another scenario where we have this system. So if you see the previous case, we had 2 poles and 2 zeros. Now what we are going to do is we are going to move this particular pole here to lie somewhere within the contour. So say this is our contour. So now it lies within the contour. So let us denote this as S0, this curve as C1, and we are going to now draw lines to get the vectors. So this particular angle, so theta 1, here we have theta 2, here this is phi 1, and this is phi 2. So now this is in the S plane. So we have the real part, imaginary part. Now let us consider the HS plane. So we have real part of h of s and imaginary part. So now if we look at this contour say will look something of this form. So both parts are symmetric. So we'll get h of s and say this particular point corresponding to s naught is s naught hat here, and this angle represents alpha. Now here what you will see as compared to the previous case is that this this alpha mean, this alpha used to lie between alpha mean and alpha max, but now here you will see this alpha will span the entire going from 0 to 2 pi, and this contour here did not include the did not encircle this origin here, but here you will see that it's encircling the origin. This is because now you have had a pole here inside the contour, whereas here all the poles and zeros were outside the contour. So what this tells us that if we just look at this particular plot, we can conclude that there is a pole in the contour in S plane. So in this contour there is a pole. So because for two reasons. The first one is this contour in h of s encircles the origin. The second reason is that here if you see, this is counterclockwise. This arrow, that is the direction in which this contour is traversed, is counterclockwise. And based on that we can conclude that there is a pole in this particular contour. So basically the idea is that if there are poles or zeros in this contour here C1, then the contour created by h of s in the, for h of s, say let us denote it as C2, in the plane h of s will have will encircle the origin. Now if this resultant contour is counterclockwise, that means there are net poles. So if there are counterclockwise, it net poles. If it is clockwise, then there are net if there are net zeros, you will get here a clockwise. So this gives us the net number of zeros and poles depending on how many loops this contour makes. So here let us consider an example. So say I am given this h of s plane, so say we have a contour which looks something of this form, and this is the direction. So you can see this is now encircling the origin. So basically there are poles or zeros in this particular contour. Now if we see, this is going, there are two loops. So one, if we project lines from the origin towards infinity, what you will see that you are encountering two loops. So basically there are either 2 poles or zeros, and since this is going both of them are going counterclockwise, we come to the conclusion that there are 2 net poles. So the idea is we get 2 net poles looking at this particular plot. Now that can mean that the contour say C1 in the S plane can have maybe 2 poles, or it could be 3 poles and 1 0. So that is the inference when we say net poles. So it gives us the difference between the poles minus the zeros. Now let us consider another case. So in this H of S plane, let us say our contour looks something of this form, and this is the direction. In that scenario, if this is the direction, since it's encircling the origin, we know there are poles or zeros within this contour, and since it's clockwise, we get 1 net 0. So within this contour there can be 1 0, or there can be 2 zeros, 1 pole. The only thing, the difference between the number of zeros and poles is equal to 1 that lie within this contour. So now here we have considered the argument principle and found, okay, this contour, how we translate it to H of S, and from that how we can conclude whether we have poles or zeros in this contour. So why is this information so important, and how can we use the argument principle to formulate our Nyquist plot? So as we had discussed earlier at the start of this lecture, we are trying to find how many, given the open loop system, trying to find how many number of unstable closed loop poles are there. So if we want to find the number of unstable closed loop poles, what we basically need to do is to ensure that this particular contour C1 spans the unstable region within the S plane, that is the entire right half plane. So our contour C1 in the S plane should look something of this one. So it should span the entire right half plane. So what we'll see is, we'll start from 0, that is S is equal to j times 0, where omega is equal to 0, and then we'll go on considering j omega, where omega then tends to infinity in the positive direction. Once we reach infinity, we'll come on by this kind of, so this here, this end represents infinity. We'll come back to the negative part, that is, so this is j infinity, j 0, and this is negative j infinity. Once we come back to negative j infinity, we'll go back to j 0. So this will be our C1 contour in the S plane. So we'll first go along the positive j omega axis to infinity, then sweep from infinity here to minus infinity, and then come back to the origin. So this will sweep the entire right half plane. So this sweeps entire right half plane. Now for an open loop system, as we have discussed, so if we for an open loop system, if there are any poles or zeros which lie in the right half plane, that is within this contour, for the corresponding H of S, that is the open loop part, we have seen that we'll get this particular contour C2 of this in this H of S plane will basically encircle the origin, and then we can get the net number of poles or zeros, which are unstable because our C1 contour is in the right half plane. So for open loop system, if the Nyquist plot, that is this particular plot, includes the origin, then we have unstable poles or zeros. Now how do we look? We have this information about the open loop system, but we want to find the number of unstable closed loop poles. So let us consider the equation we have considered so far, that is the characteristic equation for the closed loop system, that is 1 plus kg of s is equal to 0. So this particular part say represents our h of s, that is the open loop part. So we can conclude that kg of s is equal to minus 1. So earlier what we were doing, what we have seen in the argument principle, that if it, for an open loop system, if it includes the origin, that implies it's unstable poles or zeros. Now here for the closed loop system, what we are going to do is we are going to look for the encirclements of minus 1 instead of the origin 0. So for closed loop system, if the Nyquist plot includes minus 1, then we have unstable poles or zeros. So depending, as we have seen, depending on encirclements, we can conclude the net number of poles or zeros. Instead, for the open loop, it will be encirclement about the origin, whereas for the closed loop, it will be encirclement about minus 1. So now let us consider an example. So say I am given this particular, after considering the contour C1 to be the entire right half plane, as we have seen here, we get this particular contour C2 in the plane G of S. So we get something of this form. So this is the origin and this is the minus 1, and based on this we get this particular contour. So now if you see here, we can conclude its one is it encircles the origin. So the open loop system has poles or zeros, rather we can say has unstable poles or zeros. Now here we know that this is a counterclockwise encirclement. How? For that we just project lines towards infinity and we see where we get one loop, and then from that we see the direction. So we can conclude that it's counterclockwise. So basically from this we get that it is counterclockwise. So there is one unstable pole, I would rather say one net unstable pole. So this open loop system is unstable. But for the closed loop system, we find that if we project lines from -1, you do not get the contour. So basically, uh, the closed loop system is stable because there are no encirclements of -1. So far we have seen with this example about the open loop and closed loop. Now at the start we had said that we want to understand if there are any unstable closed loop poles. But so far what we have discussed is only about the basically this term which becomes the net unstable open loop or closed loop poles. So we want to find the what is the actual number of unstable poles if the system is unstable. So for that we will understand the steps for determining the Nyquist plot and number of unstable closed loop poles. So the first part is you need to plot this open loop response, say KGS, for negative G S going from negative J infinity all the way up to J infinity. Then we will evaluate number of encirclements of -1 and define that as some capital N. Next part is we will determine number of unstable poles of G of S and denote that as P. So this is the number of unstable open loop poles. So we get G of S, and finally we will calculate the number of unstable closed loop poles using the formula Z is equal to N plus P. So what does this imply? So let us consider, so I think so the first step is quite clear that we will just plot KGS and we will get those contours. Now what do the next three steps mean? So let us consider 1 plus Kg of S. So if we denote G of S, if we define it as B of S by A of S, so we can get something of this form. Then we will get A of S plus K B of S divided by A of S. So now this particular N here means the net unstable zeros of A of S plus K B of S divided by A of S. Why? Because we are evaluating the number of encirclements of -1. So that will be that contour will represent 1 plus K G of S, and here we have seen that 1 plus KGS represents something like that. Number of represents this expression, and this is basically this is basically we are looking at clockwise encirclements. So this represents clockwise encirclements, means we are looking at the net number of unstable zeros. Then the next part is poles. We just look at the, say we are given transfer function for g of s, we just find the number of, we can easily find the number of unstable poles. So this basically represents the unstable poles of A of s, because g of s is defined by b by a. So the unstable poles means is basically, you can rather say, is the unstable roots of A of s. And so we know the net number of unstable zeros. So net number of unstable zeros are the unstable roots of A plus KBS minus the number of unstable roots of A of s. So we already know what is the number of unstable roots of A of s. So from that we can find, if we basically just add these two expressions up, that is n plus p, then we can find basically the unstable roots of A of s plus kb of s, and this particular expression is equal to z because the unstable roots of A of s plus kb of s is basically represents the unstable closed loop poles, because the poles of 1 plus kgs are basically the roots of A of s plus kb of s. So we can say from that, this deduction, we get z is equal to n plus p. So we will consider an example. So let us consider g of s is equal to 1 divided by s plus 1 the whole square. So first thing what we will do is, the first step, you can see we need to make a plot. So towards doing that plot, we will evaluate g of s at, say let us s is equal to j omega and omega is equal to 0. So in that case we get g j0 is basically equal to 1 divided by j0 plus 1 the whole square, which is equal to 1. Next we evaluate g of s at omega tends to infinity. So in that scenario, what we will get, that the limit omega tends to infinity, g j omega will basically get 0. Now we have calculated, we get these two values, one at omega is equal to 0, omega is infinity. Now we want to understand what happens between infinity and 0. So we will find that we need to find, if we need to plot this in the g of s plane, we need to find what are the real and imaginary intercepts. So we consider this particular expression. So this is given by 1 minus omega square plus 2 j omega, which is equal to 1 minus omega square the whole square plus 4 omega square, and numerator will get, so we multiply this by the denominator, the complex conjugate of this denominator both in the numerator as well as denominator to get this expression. So the denominator then becomes a real number, whereas the numerator is complex number, and we can split it up into real plus complex, real plus imaginary part. So now what we can do, we can set real part to 0, and that implies that omega is equal to plus or minus 1. And so based on this we can get that the imaginary part is equal to plus or minus half j. The next part, we set the imaginary part to 0. So that gives us basically omega is equal to 0 or infinity, and we have already the expressions for that. So if it's 0 it's 1, infinity is 0. So we have now calculated these particular values. Now we are going to plot this Nyquist plot. So basically we start from here. So this is 0, this is 1, and this part represents s going from 0 to basically j omega. So at s is equal to 0 we are at 1 and infinity. This is 0 to j basically, sorry, j infinity. So at 1 value of s is equal to 0, at j infinity the value of g, this contour goes to 0. So basically the direction will look something of this form, and here we will have this particular form as we have seen is 0.5 j. So we will have minus 0.5 j. Now similarly coming to the other half where we go from negative j infinity to 0, that will be symmetric about this axis. So get here this is 0.5 j. So this is what the contour looks like. So now once we have this contour, what we will try to do, we will see where is minus 1. As we have seen here, the next step is to understand how many clockwise encirclements of minus 1 we have. So we see that this contour does not encircle minus 1. Sorry for that. So here we see this does not encircle minus 1. So n is equal to 0. The next step, as we have seen here, is to determine the number of unstable poles of g of s. So if we look at the number of unstable poles by looking at the transfer function, we find that the poles there are repeated poles at minus 1. So this basically is a stable system. So even the open loop system is stable, so we can conclude that p is equal to 0. So this implies that z, which is the summation of n plus p, that is z is basically the number of unstable closed loop poles and is summation of n plus p, we come to the conclusion that z is also equal to 0. So this closed loop system is stable for all values of k. So this we can conclude from the Nyquist plot. So how can we verify this? So let us have a look at a technique which we have learned in previous lectures, which is called the root locus. So this is the S plane now. So our system, open loop system, is 1 divided by S plus 1 the whole square. As I said, there are repeated poles for the open loop system. So this is at minus 1, and so there are 2 poles, you can say, no zeros. So both branches, so there will be 2 branches, both going to infinity. If we look at the real axis, uh, there is no part of the real axis which is contained in the loci. So no part of loci lies on real axis, and for the asymptotes, since it's going to infinity, the asymptotes will be at alpha is equal to minus 1, phi 1, that is the angle of first asymptote, will be 90 degrees, whereas phi 2 will be 270 degrees. So this represents asymptotes are emanating from minus 1. So you'll have one asymptote here, and the other one, the first one 90 degrees will move upwards, 270 degrees will go downwards, and from this we can get the root locus looks something of this. So this is our root locus. So even now, if we look at the root locus, we'll find for all values of k, what we have come to the conclusion that for all values of k, this closed loop system is stable. So now we'll move on to another example. So let us consider g of s is equal to 1 divided by s into s plus 1 the whole square. So we'll take s is equal to j omega, and we'll vary omega from 0 to infinity, negative infinity, and we want to draw the contour because that's the first part of drawing the Nyquist plot. So if we substitute omega is equal to 0, what we'll get is this tends to infinity, whereas when omega tends to infinity, this is equal to 0. Now coming to setting the imaginary part is 0. So corresponding to that, we'll get the real intercepts will be equal to minus half and 0. So this corresponds to the condition that omega is equal to plus or minus 1, whereas this, as we have seen here, omega tends to infinity. Now if the real part is set to 0, the imaginary intercept will be at 0. So basically the same, that is that the origin omega tends to infinity. So based on this, we can draw the Nyquist plot. So this is what our Nyquist plot looks like, and this is basically represents the part where we have seen that is at omega is equal to 0 goes to infinity. So this dash part represents the infinity part, and here we have omega greater than 0, here we have omega less than 0. So at plus or minus 1 omega, it's at minus half, as we have seen here, and here we have at the origin omega tends to infinity, and this is what our Nyquist plot looks like. So we'll get this, it goes in this direction, then this, and finally something of this form. So if we look at minus 1, this is where minus 1 lies. Now from this equation, that is 1 plus kgs is equal to 0, we can get gs. What we did was kgs is equal to minus 1, so we were considering minus 1. Now if we just, so here to consider minus 1 for different values of k, we will have to keep on scaling this and then see if it encircles or not. So one idea is to just draw one plot for g of s instead of kg of s, and we consider this kind of equation. So instead of checking for encirclements of minus 1, we check for encirclements of minus 1 by k. So basically if we see here, so here we'll see there are two parts, one which lies from if minus 1 by k is between 0 and minus 0.5, and one where it is beyond minus 0.5. So if it's between 0 and minus 0.5, what you will see is that say it's somewhere here, this represents minus, sorry, so say this represents minus 1 by k. So if we are considering this, what we'll do is we'll project lines outwards towards infinity, and what you will see that there are basically two clockwise encirclements. So that denotes that in this region between 0, so let us say minus 1 by k is between 0 to minus 0.5. So what you will see is that n is equal to 2. If we look at our closed loop system, we can at our open loop system g of s, we can conclude p is equal to 0. So this implies that z is equal to 2. So there are, if for this particular values of gain, that is for, if we from this equation we conclude that k is greater than 2, that implies that there are two unstable poles in the closed loop system for k greater than 2. Now we consider beyond minus 0.5, that is k is less than 2. What you will see is if we project, say this point lies somewhere here and we are just projecting here, you will see that there is one counterclockwise encirclement and then there is a clockwise encirclement. So they both cancel each other out. So we'll get n is equal to 0, and from here we can see p is equal to 0, so z is equal to 0. So this represents, when k is less than 2, represents a stable system. So now let us verify this using a root locus plot like we did for the last example. So in the S plane we have real imaginary part here. So for this particular system we have one pole here and there are two repeating poles at minus 1. So this is 0, minus 1. So as you see, 3 poles, no zeros, all branches go to infinity. So if you see a particular the loci on the real axis contains the negative real axis. So the entire negative real axis is part of the loci. And if we consider alpha, we get minus 2 by 3, and the angles are 60 degrees, 180 degrees, 300 degrees. So basically here we will have 60 degrees, 300 degrees, and what is going to happen is one of the loci will start from minus 1 . So this asymptotes will start from minus 2 by 3. So that will be, say, somewhere here. So we'll have one here, the other one coming here. So basically one of the loci will start from here minus 1 and go up to along the negative real axis, whereas the other one will come here and go to this point, and from here it will go along this asymptote. The other one will start from the origin, maybe take this path. So here we see that this one of these poles will have a root loci which is always stable because it goes up to negative infinity along the real axis starting from minus 1. Whereas if we look what happens here for the other two is that there will be some unstable part, and that is at values k greater than 2. So for k greater than 2, it becomes there are two unstable poles, and that is what we can also see from the Nyquist plot. So this verifies our Nyquist plot. So we have now seen the argument principle, how to plot the Nyquist plot, and a couple of examples, and compared them with root locus. So now we'll focus on the last concept for today, that is understanding the margins. So we had discussed margins when we discussed Bode plots, right? That was one gain margin and phase margin, which give us an idea of what's the how close we are to instability. So let us see what so we had seen that it is based on the characteristic equation, that is 1 plus kgs is equal to 0. So kgs we can conclude is minus 1. So if we kgs this equation, we can say that the instability like and minus 180 here, this minus 1, so basically it lies on a unit circle. So this is our point of interest. Now let us say I have a Nyquist plot which looks something of this form. So based on this we can conclude, we want to understand, we know that at minus 1 this condition is satisfied, represents kind of the border stability. So the gain margin, that is GM, is basically defined in this manner. So GM is the gain margin, whereas the phase margin is basically represented where this particular Nyquist plot intersects this unit circle. So that angle, this point, is given as the phase margin. So basically, similar to Bode plot, we can use the Nyquist plot to calculate the gain margin and the phase margin. So to conclude, we can say that we can use this Nyquist plot to predict number of unstable closed loops poles and the gains at which, if there is a, they might become unstable, and how many poles we have in the unstable region. And we can also calculate what are the gain and phase margins. So today we studied about the argument principle, plotting Nyquist plots. We did a couple of examples and compared them with root locus, and finally we concluded with margins. Next class we will study about state space. That's all for today. Thank you.